My name is Rodrigo Thiers, and today I will present some of the work that I developed during my PhD with my supervisor Christian Marga-Chukitaipe at Imperial College London, which deals with the seismic protection of rocking structures, timber buildings in particular in this case, with inertors. So I would like to start with a very quick review of the fundamentals of seismic design. Traditional seismic design methodologies aim to ensure life safety during a design level earthquake, which is typically associated with a 10% probability of exceedance in 50 years. In this framework, specific zones are designed to yield and concentrate the majority of the lateral deformations, thus limiting the forces that the structure can experience during an earthquake. As a consequence, structural damage is permitted and indeed expected in these critical sections. In the case of timber structures, ductility is provided by steel connectors, while timber members are capacity designed to ensure that they remain in the elastic range. Although in general this design philosophy has succeeded in preventing structural collapse and protecting lives, recent earthquakes have revealed that in many cases the extent of damage can make repairs unfeasible, highlighting the mismatch between social expectations and the observed seismic performance of civil structures. Over the last years, performance-based design objectives have shifted towards damage control and continuity of operations after a design-level earthquake. In this context, the advantages of rocking behavior have been applied to the development of a family of self-centering systems that can sustain large lateral deformations with no significant damage. In the case of wall structures, like the one represented here in the figure, overturning moments are resisted by gravity loads and vertical post-tension tendons that can be provided to ensure that the system has a positive post-uplift stiffness. This is represented here in the figure on the right, where the black line represents a freestanding rigid block with a negative stiffness, and the green line represents a block with a stiff tendon, which takes the stiffness to a positive value. Once the decompression moment is exceeded, a gap begins to open at the base, concentrating most of the rotation demand, while the rest of the structure remains completely elastic. Additional external dissipators can also be added to increase the energy dissipated by the system, like the U-shaped flexural plates shown in the figure here on the left. This configuration has been used in different timber buildings in seismic regions, mainly in New Zealand, like the picture shown here on the right, for example. Although these systems work very well preventing structural damage, previous studies have demonstrated that higher accelerations associated with impact at the base can develop throughout the structure, compromising the overall performance of the building. Figure A presents the base rotation response, and the instant of impact is indicated here with a dashed line. Figure B on the right shows the horizontal acceleration response at the first 3 mass levels. It is clear here that impact generates high-frequency vibrations that result in increased accelerations. As a result, even when subjected to low-frequency pulses, impact forces can excite higher vibration modes of the uplifted system and generate significant acceleration demands. One alternative to control these high-frequency vibrations is the incorporation of a mechanical device called inerter. The inerter develops a resisting force which is proportional to the relative acceleration between its terminals. Although several types of inerters have been proposed and patented, the general properties of the system can be studied by considering the particular case of a rack pinion flywheel device like the one shown here on the figure on the left. The system consists of a series of flywheels connected to a linear rack through a pinion gear mechanism. By evaluating rotational equilibrium, it can be demonstrated that the apparent mass of the system, or inertance, is given by the expression on the middle here, mr, which can be several orders of magnitude larger than the actual gravitational mass of the device, and that's one of the main advantages of the inerter. The inerter can also be combined with a clutch, as shown on the figure on the right, to ensure that the device only opposes and doesn't drive the motion of the structure. In this study, the ability of the inerter to control the rotation amplitude and suppress higher Mohs effects is applied to the seismic control of rocking timber buildings. To this end, a 6-story case study building was designed following direct displacement-based design guidelines. The structure is formed of rectangular modules of 12 by 10 meters and has an interstory height of 3 meters. The structural plan consists of a frame in the transfer direction supporting gravity loads and 4 post-tension CLT walls providing lateral load resistance in each direction. External steel dissipators are also added at the base of each wall to increase the energy dissipation capabilities of the system. The timber rocking walls were designed for a top story drift of 1.2% as target displacement. The design spectrum was taken from Eurocode 8, considering a high seismic hazard, a stiff soil, and a peak ground acceleration of 0.4 g. In this methodology, the 5% damp displacement spectrum is reduced to account for the hysteretic damping of the nonlinear structure. This is shown on the left figure, where both spectra and the design point are plotted. The rocking section at the base was designed following previously developed guidelines based on the monolithic beam analogy. The forces acting on the section are shown above figure B, which also shows the characteristic flag-shaped hysteretic loop of post-tension rocking systems. For the design of the inertors, a ball screw and gear configuration was considered. In this configuration, a ball screw mechanism is used to transform the linear motion of a rod into a rotation in a flywheel. A gear system is also included to further amplify the rotational motion, while a clutch can be incorporated to ensure that the inertor only opposes the motion of the structure. Since clutch inertors can only oppose one direction of motion, a pair of parallel devices is required in these configurations. Two levels of mass ratios are considered, 1 and 2, which are defined as the inertance over the total mass of the structure. The inertors are considered to be supported on a rigid steel chevron frame and connected to the first floor diaphragm. The results of the design are presented in this table, where we can see that the apparent mass of the device is approximately 10,000 times larger than their gravitational mass. The numerical model used to represent the rocking walls consists of three components: the deformable body, the rocking surface, and the underlying soil. Linear elastic beam column elements are used to represent the flexible structure, whereas a zero-length fiber section is considered for the rocking surface. A compression-only material is assigned to the rocking section, so the system is free to rotate about the pivot points. Energy loss during impact is incorporated by taking into account the energy radiated into the underlying ground. Accordingly, the structure is assumed to rest on a rectangular rigid foundation, while the soil underneath is represented by a set of vertical, horizontal, and rotational springs and dashpots whose mechanical properties are determined according to standard machine vibration theory. Additionally, a numerical representation was developed for the inertor. This approach is presented on the right, where two nodes are connected through a rigid link and an angular mass J is assigned to the rotational degree of freedom at node 1. In this way, the relative lateral displacement between the nodes is transformed into a rotation in node 1. The reactive force developed by the model is proportional to the horizontal relative acceleration between the nodes, which represents then an inertor. And the parameters of the model, J and ρ, are then defined in terms of the inertance Mr according to the equation here at the bottom. Each structural model was first subjected to a set of 7 different earthquake records. The records were chosen so the mean spectral displacement demand is consistent with the design displacement spectrum within the period range from 0.1 seconds to 2.5 seconds. This range of periods was chosen to include at least the first 3 elastic modes of vibration of the 6 stories building and the effective period of the substitute single degree of freedom structure. The figures here on the slide show the acceleration and displacement spectra of the ground motion subset and the spectrum considered during the design procedure. The figures on this slide present the response of the unprotected building to the set of 7 ground motion records. The black line represents the design values, and the red line is the mean response obtained from the response history analysis. The results of the analysis showed that the DDBD procedure adequately estimates the mean lateral displacement of the building, with differences of around 4%. These small deviations are likely related to a misestimation of the hysteretic damping obtained with the area-based approach. The shape of the displacement profile, on the other hand, is reasonably described by the design assumption. The moment at the base of the walls is limited by the strength of the rocking section, and therefore is very similar to the design value. On the other hand, bending moments above the base and shears throughout the structure are significantly underestimated by the design procedure. This shear and moment amplification are caused by the response of higher modes of vibration which were not directly accounted for in the displacement-based design procedure. A first assessment of the effect of the inertors on the response of the case study structure was conducted considering the same 7 records used before. These figures compare the mean peak displacement, floor acceleration, interstory shear, and bending moment demands of the unprotected building with those of the inertor-equipped ones. Total lateral displacements around 10% lower are obtained in the case of the protected buildings, while an efficient control of higher mode effects is also observed. This is reflected in significantly lower peak floor accelerations and reduced bending moments above the critical section. Although the control of the higher modes response also reduces interstory shears in the higher stories, the connection of the inertor to the first story diaphragm significantly amplified the shear force in the ground level. As I mentioned before, a clutch can be incorporated into a system to ensure that the inerter can only resist and not drive the motion of the structure. Since a clutch inerter can only oppose one direction of motion, the total apparent mass ratio of the parallel inerters designed before is halved when the clutch is incorporated. Then the response of the structures equipped with clutch inerters is compared with that of non-clutch inerters of twice the apparent mass ratio. Although the introduction of a clutch reduces the total apparent mass ratio of a given pair of parallel inerters, the ability of the system to control the displacement response of the structure is not significantly affected, as it can be seen here in the first figure on the left. A similar trend is observed in the floor accelerations and bending moments distributions, where peak values of comparable magnitude are obtained along the height of the wall system for both inertia configurations. Crucially, a mild reduction in the shear force at the ground level is observed for the structure equipped with clutch inerters, reaching magnitudes even lower than in the unprotected case. This observation suggests that the shear amplification observed in the non-clutch inerter cases is related to a surge in the resisting force as the device drives the structural motion. A crucial consideration for the proposed system is that the resisting force developed in the inerter devices must be transferred to the ground and to the floor diaphragm. For this, the inerter devices are supported by a reed steel frame and connected to the floor diaphragm through a screwed steel plate. Replaceable fuse elements are incorporated in order to limit the resisting force that can develop in the inerter and protect its mechanical components and the steel timber connection. The connection was designed according to Eurocode 5, considering an apparent mass ratio of 2 for the non-clutch device and an apparent mass ratio of 1 for the clutch one. The fuse elements were designed for the inerter forces obtained from the previous response history analysis, and the connections were capacity designed. This table shows the dimensions of the plates and the number of bolts for each configuration. Finally, a performance-based assessment with particular emphasis on non-structural and contents damage was conducted considering a database of 202 pulse-like ground motion records obtained from the Thiers database. The figure on the left shows the distribution of magnitudes and distance to the ruptured area of the records, and the figure on the right shows the corresponding acceleration spectra. Limit states associated with extensive non-structural and contents damage were defined for the lateral drift and peak floor accelerations. The interstory drift limit defined in Eurocode 8 for buildings having ductile non-structural components, which is a drift of 0.75%, is adopted for displacement-sensitive elements, whereas a floor acceleration limit of 1g is defined for acceleration-sensitive non-structural components. These figures compare the fragility curves obtained for the different case study structures and limit states under consideration. The 5% damped spectral acceleration at the first fixed base structural period is used as intensity measure for the interstory drifts, whereas the peak ground acceleration is considered for the peak floor accelerations. The results of this assessment are in line with conclusions obtained in previous analysis, showing that structures equipped with inerters experience lower probability of exceeding the defined limit states. Overall, our results allow us to conclude that inerters can be used to improve the seismic performance of a wide range of rocking structures, including post-tension timber buildings. Thank you very much for your attention, and please do not hesitate to contact me if you have any questions or comments about this presentation. Thank you.